Nothing travels faster than the speed of light. You've heard this before, right? It's like the ultimate cosmic speed limit, 299,792,458 meters per second. The universe's ultimate "you shall not pass" moment. But what if I told you there are things that do stick around, and I'll explain what they have uncovered. Now, before you start planning your faster-than-light vacation to Alpha Centauri, let's be clear. Some of these are clever illusions, some bend the rules in fascinating ways, and others exist only in the realm of what if. But all of them will make you question what speed really means. Today, we're diving into the cosmic exceptions, the quantum weirdness, and the theoretical possibilities that push the boundaries of Einstein's speed limit. From the expanding universe to quantum tunneling, from shadows that outrun photons to hypothetical warp drives. Buckle up for a mind-bending journey through the fastest phenomena in the cosmos. Let's start with the biggest rule breaker of all, the universe itself. Right after the Big Bang, during a period called cosmic inflation, space expanded so rapidly that regions of the universe moved apart from each other, faster than light could travel between them. And here's the kicker. It's still happening today with the most distant galaxies. But wait, didn't we just say nothing can go faster than light? Here's where it gets beautifully weird. Imagine you're baking raisin bread. As the dough rises, the raisins move apart from each other. Not because they're running through the dough, but because the dough itself is expanding. The raisins aren't breaking any speed limit for raisins moving through dough. The medium they're sitting in is just getting bigger. Same thing with galaxies. They're not zooming through space faster than light. Space itself is expanding between them. It's like drawing dots on a balloon and inflating it. The dots move apart, but they're not actually racing across the balloon's surface. Einstein's speed limit applies to objects moving through space-time, not to space-time itself, stretching. The universe found the ultimate loophole in its own laws. It's not breaking the speed limit, it's rewriting the road. This is why we can observe galaxies whose light has been traveling toward us for over 13 billion years. Even though they're now more than 13 billion light-years away, the space between us and them has been stretching the whole time, carrying them beyond the distance light could have normally traveled. Space, 1. Speed of light, 0. Now let's shrink down to the quantum realm, where things get spooky. Einstein called it spooky action at a distance, and he wasn't comfortable with it. But quantum entanglement is real, and it seems to connect particles instantaneously across any distance. Here's the best way I can explain it. Imagine you have two magic dice. You give one to a friend and keep one yourself. Now, no matter how far apart you go, even to opposite ends of the galaxy, whenever you roll your die and get a 6, your friend's die will instantly show a 1 every single time. The correlation is perfect and immediate. That's essentially what entangled particles do. Measure the spin of one particle, and its entangled partner immediately knows to be in the opposite state, even if it's on the other side of the universe. But here's the crucial catch that saves Einstein's speed limit. You can't use this for communication. You can't control what you'll measure. It's random, so while the correlation appears instantaneous, no usable information travels faster than light. It's like having those magic dice, but you can't choose what number you'll roll. Your friend sees their die change instantly, but they have no idea if you've rolled yet or what message you might be trying to send. The universe maintains its no faster than light information rule, even while allowing this mysterious quantum connection. Quantum entanglement doesn't break the speed of light. It just shows us that the universe is far stranger than our everyday experience suggests. Sometimes, waves themselves seem to cheat the system. In certain materials, you can create conditions where the peaks of waves appear to travel faster than light. Think of the wave at a sports stadium. The wave itself races around the stadium much faster than any individual person could run the same distance. The people just stand up and sit down in sequence. They're not actually moving around the track at all. Similarly, in specially engineered materials, the phase velocity, the speed at which wave peaks move, can exceed the speed of light. But the group velocity, the speed at which the actual information or energy travels, stays safely under the cosmic speed limit. It's like the wave peaks are just the visual effect racing ahead, while the real message takes the normal, law-abiding route. The universe allows the illusion of speed while keeping the substance in check. You can make wave peaks dance faster than light, but you still can't send your friend a faster-than-light text message. In the quantum world, particles can do something that would make video game players jealous. They can tunnel through walls. Imagine throwing a ball at a brick wall. Classically, the ball bounces back. But quantum particles, sometimes they just appear on the other side, as if the wall wasn't there. This is quantum tunneling, and some experiments suggest that when particles tunnel through barriers, they seem to cross in zero time, or even negative time. The particle spends so little time inside the barrier that it appears to have crossed faster than light, but once again, the universe protects its speed limit. The tunneling process is probabilistic and random. You can't control which particles will tunnel or when, so you can't use it to send information faster than light. Quantum tunneling happens constantly in your electronics and even powers the nuclear fusion in our sun. But despite these quantum shortcuts, no usable signal travels faster than light. The universe allows particles to take quantum shortcuts while still respecting the information speed limit. Here's a fun thought experiment. Imagine you have a laser pointer, powerful enough to reach the moon. Now quickly sweep it across the lunar surface. The dot of light races across 3,476 kilometers of moon surface in just a fraction of a second. Do the math, and that dot is moving way faster than the speed of light. But what's actually happening? No. Individual photon is traveling that fast. The photons are just taking the same old 1.3-second journey from Earth to Moon. It's just that different photons are hitting different parts of the moon as you sweep the laser. It's like moving your finger across the night sky and claiming your finger traveled trillions of kilometers per second. The connection between where you're pointing moves fast, but no actual matter or energy is making that journey. Same thing happens when you close a pair of scissors. The point where the blades meet can race along faster than light, but no part of the scissors is actually moving that fast. These are beautiful examples of how patterns and illusions can appear to break the speed limit while respecting the deeper physical laws. Ever wondered why nuclear reactors have that gorgeous blue glow? That's Cherenkov radiation, and it happens when particles do go faster than light, sort of. In water, light slows down to about 75% of its vacuum speed due to the material's refractive index. But high-energy particles from nuclear reactions can still travel at close to the vacuum speed of light. So these particles are moving through water faster than light moves through water. Just like a jet creates a sonic boom when it breaks the sound barrier, these particles create a kind of photonic boom, a beautiful blue shockwave of light. But the cosmic speed limit still holds. These particles aren't going faster than light in vacuum, just faster than light in that particular medium. It's like driving 70 miles per hour in a 55 miles per hour zone, while still obeying the national speed limit of 80 miles per hour. The universe has local speed limits, and sometimes they're lower than the ultimate cosmic one. Now let's venture into science fiction territory. In 1994, physicist 𝗦𝗫𝗄𝗫𝗓 published a paper describing how you could theoretically travel faster than light without actually moving faster than light. Welcome to the mind-bending world of warp drives. Here's the idea. Instead of pushing your spacecraft faster and faster through space, you manipulate space-time itself. You compress space in front of your ship and expand it behind you. The ship itself never moves faster than light through local space. It's riding a wave of warped space-time. Think of a surfer riding a wave. The surfer isn't swimming faster than the wave's speed. They're being carried by the moving water. Similarly, a warp drive would be carried by moving space-time. But there's a catch. Actually, several catches. The energy requirements are astronomical. We're talking about the mass and energy equivalent of Jupiter converted entirely to energy. And you'd need exotic matter with negative energy density, which may not even exist. Recent research has tried to reduce these requirements, and some physicists are seriously investigating the physics of space-time manipulation. NASA even had a small research program looking into it. So while we're nowhere near building a warp drive, the universe's laws don't explicitly forbid it. The speed limit applies to moving through space-time, not to manipulating space-time itself. Once again, the universe might have left us a loophole. Finally, let's talk about the ultimate speedsters, tachyons. These are purely hypothetical particles that would always travel faster than light. Not sometimes, not under special conditions, always. In fact, according to the math, they couldn't slow down to light speed any more than we can speed up to it. Tachyons would have imaginary mass, not imaginary like made up, but mathematically imaginary involving the square root of negative numbers. They would experience time differently, potentially even going backward in time from our perspective. The problem? We've never detected one. Despite decades of searching, tachyons remain purely mathematical curiosities. They're allowed by some interpretations of physics equations, but that doesn't mean they exist. They're the darling of science fiction because they would enable all sorts of causality breaking, time travel shenanigans. But so far, they remain in the realm of what if, rather than what is. So, what have we learned? The universe is far more clever than we give it credit for. Some things only appear to go faster than light, like shadows racing across the moon or wave peaks in special materials. Others, like quantum entanglement, show us that reality is deeply connected in ways that don't require faster-than-light travel. The expanding universe and potential warp drives remind us that space-time itself can bend the rules without breaking them. Einstein's speed limit remains unbroken as a fundamental rule for information and causality. But the universe has found beautiful ways to dance around it, creating phenomena that stretch our understanding of speed, space, and time. Maybe we'll never send messages faster than light or travel to distant stars in the blink of an eye. But in trying to understand these cosmic exceptions, we've discovered that the universe is far stranger, more beautiful, and more interconnected than we ever imagined. The universe may respect light's speed limit, but it doesn't stop us from dreaming about what lies beyond it. And who knows, maybe our dreams will show us loopholes we haven't discovered yet. If you enjoyed this journey through the fastest phenomena in the cosmos, give this video a like. Share it with fellow space enthusiasts, and subscribe for more mind-bending explorations of our incredible universe. What would you do if you could travel faster than light? Let me know in the comments below. Until next time, keep looking up and keep wondering what's possible.